Right, so back for part 2 of the video. Gravity. What is it? How does it work? I think Einstein's been proven right on most of his work. They won't tell you about the mistakes he made. They were only minor, you know, like an example would be gravitational waves would dissipate and be meaningless over a much shorter distance than what they actually... So he only made a minor error. The truth is gravitational waves propagate forever, basically. Almost forever. Remember, nothing can be infinite. No such thing as true infinity. So let's see, what could cause this gravity? It's definitely a field. We can prove that just by mapping out space-time. And by the way, the old name for space-time was ether, the ether out in space. They knew something was there, and that was, well, you can easily say that space is filled with the odd particle here and there. You could say it's filled with electric fields and magnetic fields and gravitational fields. There's all sorts of stuff happening out there in space. So let's draw what we call a gravitational field. We'll draw a planet, approximation to Earth. It's a bit distorted, at least it's not flat. And we'll draw a recognisable continent. Something like that. That'll do. Bit of Asia there. Maybe India's around the corner. Antarctica. North Pole. I think South America would be sort of over there. Maybe the USA up there. Crude drawing, but it doesn't matter. So the gravitational field around this planet, it's what I call the near field. So I'll write that in here. Near field. Okay. The near field is caused by the local object. The opposite field to this is the far field, and this is what people have, I don't think they've taken it into consideration, and this is the gravitational field. The far field is the resultant gravitational field of every other particle in the universe. So the far field is, well, we've got a very small universe at the moment. That's your universe. It shrunk, alright? Or it's only a few seconds after the initial creation of it. Okay, how it works is, I'll just drew one gravitational ray. That's right, I said a ray, because that's how humans express things. We express things in relatable numbers, drawings, graphics, that sort of thing. So this line here is actually two lines. I'll draw a red line. They don't sit parallel to each other in real time. They actually are superimposed over each other. But I will just draw it side by side for clarity's sake. And there is your gravitational field right there, or two lines representing. So really they're not lines, there is no such thing as gravitational lines, but these are fields, and these two fields interact. Now if you've got an object out here and you want to move it, there's no, when you're close to here, there's no influence from the Earth, but there's still inertia. And what causes the inertia? The far field. I better write that back in. The far field is responsible for inertia in mass. Now, as you'll note, I will not do any math, because if I start doing math, it will take up this board, the next board, and I'd have to get some more boards in, and it would just be pages of meaningless symbols and numbers, and only a mathematician would be able to say, oh yeah, I'm following that. Oh no, he's got that wrong. Or no, wait. Oh, wait. So we can express all this in numbers, but it's better to give you a picture, like a cartoon, to immerse you into it slowly, because this took years and years to develop. And how did I develop it? Well, I had what you'd call a close encounter of the first kind years ago. I might tell you about that if anyone's interested. It's imprinted in my memory like it happened yesterday. But anyway, I was out to solve a problem for almost, it's 39 years, around about now, yeah, it's 39 years have gone by since I saw what I saw, and I thought, how does that work? And it took me a lot of study. I studied things I didn't ever think I would want to study. But so asking gravity, what is it? It's not a force, it's a field. It's actually a dual action field. Let me put this to you. Have you ever seen a battery with one terminal? No. Have you ever seen a magnet with one pole? No. Everything has two poles. And this is where the exchange here is. This is the near field, the far field. This does not have to know where this is. And the far field does not have to know where this is. Because they have been joined since the universe came into being. Right from the beginning. These lines were there, or the fields were there, and my representative lines could have been drawn way back then as well. And if you want to get into the math of it, these get thinner as they get further out, and down this end they're thicker, and these lines here, the far field lines are thin, and I think I calculated them out once. I think that's something like, watch this, say 1.0 times 10 to the 1800. That's just approximate. I can't remember the actual number, but I know it was like nearly almost 2,000 to the power of 2,000. So if you were to write that out in very small numbers, that number would probably be 2 or 3 kilometres long. That's a ridiculously large number, and it takes into account every particle in the universe that we know about. Now, I'm emphatic about that. We know about. We don't know much about our universe. You've got scientists out there with Hubble and James Webb Space Telescope. Thanks for that, guys. I was waiting for that for over 10 years, and the pictures have been pretty good, but yeah, I think you're going to need a bigger one, a much bigger one, something like 10 times the size of James Webb. Anyway, getting back to this gravity thing. This is quite easy to solve once you work out it's two separate fields. I still haven't told you what gravity is. Well, I'm giving you an overview. Gravity warps space-time. Space-time does not create gravity. It's the opposite way around. I really am adamant that that's my view. Now we got back to this far field. If you took the planet away, we'd only be in a far field. The only near field would be your body or your spaceship or whatever you're in. So we'll take that away. And we can prove the existence of this far field. Very easy. Voyager 1, Voyager 2, Pioneer 1, Pioneer 2, all the Mars missions, all of them proved that this far field exists. Why? Because they all carry gyroscopes. And a gyroscope, draw it like this. No, that's not right. So there's our gyroscope, pretty crude. What's the secret to a gyroscope? In the far field or anywhere in the universe, that gyroscope, once spinning, once aligned, apart from mechanical drift and that, the gyroscope will attempt to maintain rigidity in space. That is the most important thing I could tell you. That gyroscope, the spinning gyroscope, will maintain its orientation in deep space. Okay? Now that tells me that this is interacting with the gravitational field, and the gravitational field is somehow, I don't know the mechanism yet, but I do know if we add a few magnets and a few coils and we spin this up and we do something else, and we can build a complicated machine that generates its own gravity. Now, I will take bets on this. So now we've got a machine that somehow is interacting with gravity. Okay? That's a pretty big major step. We've had them for years. People will tell you that they keep it this way or can do this, or they will not explain to you fully how it maintains its orientation. You can say, oh, it's force and this and that. You know, getting back to the gravitational field, I'll do a bit better drawing for you, and I'll show you the gravitational. We'll break it down into lines because that's easy for us humans to understand. So I'll just grab a drink. G'day viewers, continuing on from my last video. Where are we? Right, these are spatial sectors. This is supposed to be a cube, and this is well, it's like an inverted pyramid section, and these are the same two tensor sectors, but in different types of space. This would be in the far field with no near field distortion, so it's out in the middle of space, nowhere near a planet or asteroid or anything, and it has a cubic shape. Now when this sector comes in contact with a near field, a large object, a planet, moon, even a large asteroid, anything it will start to distort like this. This is actually something that would be represented on near a black hole. Depending on the size of the black hole, would depend on the angle that this pyramid forms. So down here, this actually demonstrates spaghettification, and as you can see, well, most people think these would be three-dimensional tensors. You can have them as three-dimensional if you like. They're actually four-dimensional tensors. So it's a 4x4 matrices, 4x4 matrix, and you have to use matrices multiplication. I'm not good at it. I use a computer to do it. I think most people would. You'd have to be a math genius to work this out without a computer. So, and in my defence, Einstein himself hired a mathematician, and which I don't really need a mathematician. I've got computers that'll do this, and most of you already will have. So this is what happens. The closer you get to the near field, the more it condenses, and this is where your time slows down. And as you know, time is the fourth dimension, and it is a dimension because the word dimension really means measurement. Okay, so there's a measurement of time and a measurement of spatial coordinates, and of course your three dimensions. And what'll really freak some people out is some people calculate these as 8-dimensional quasi-crystals, and the information that I have points them to being 12 dimensions. So that's really mind-blowing stuff to us mere humans. But what I'm getting at to here is this is all the result of an actual experiment. The one experiment, I was able to glean so much data and so much information that it just said, this is gravity, this is what it is, this is how it is. So this is my interpretation to present to all you people out there. Some people might agree with it. I think most people won't agree with it. But anyway, this is what gravity does to space. Low gravity or neutral gravity out in the far field. This is sitting next to a planet or a black hole. A planet wouldn't be this exaggerated. A planet you'd barely notice. There'd be less than a 1 degree convergence on the angles of the pyramid. Something like this, you'd be looking at a supermassive black hole to create that much distortion. But I exaggerated it here for your appraisal. So how did I get to this? How did I get to all this? Because I conducted an experiment based on an actual observation, and I sort of reverse engineered what I saw to, I don't want to give too much away, but this is based on an actual observation that led me to make several experiments. Many of them failed before I got to the successful one. And I know China and Russia and maybe even the US are working on these sort of problems. And I know for a fact, because there was some leakage from one of the top secret groups. Oh yeah, it's all top secret, I can't tell you any more than that. Of course they like to brag, you know, they like to let it out that, oh, they're so far in front of us. They had an 8% reduction in gravity, 8%. I think the Chinese were about the same. I'm pleased to say right now that I achieved over 100%. So if that means anything to you, to me it means positive lift. But anyway, that's my little explanation of what's going on. I don't know if I can tell you much more without giving you much more. Anyway, we'll talk about maybe some experiments later. I don't really know where to take this from here. I can build the machine in probably less than 90 days, a full-size, let's leave the Planet machine. I could build the engine in 90 days anyway. Yeah, so that's it. That's my explanation and how it works. And if you want to create a force, it's not really anti-gravity, it's gravity, but it's just in reverse. I mean, you call it anti-gravity, but no such thing as anti-gravity. It's just, well, yeah, you would call it anti-gravity, but it's just an opposing force. And how it works is, instead of pushing up, which is what you'd naturally think would be the way to create anti-gravity, no, that's not the way to do it. In the, I'll just draw it here, it's probably easier. So if this here, if gravity's here like this, and these parallel lines, and they do V equals C, the velocity equals C, right? So what we've got to do is, we've got to do this. And what is that? That means we've tried to exceed C, we've tried to accelerate this faster than C, and what happens? You can't. You cannot exceed C, so these lines straighten out up like that, and that is resulting in lift. So that's my little demo, my little explanation. If you want me to go into it further, I can, but I can't show you the machine. I've only got part of the machine built, and the part that I have built is the actual lift generator, and I need to encapsulate that inside an engine housing so we can give it the lift. And if I know there's a lot of people built some crazy looking machines, and none of them have achieved 100% lift, and I'm way above that. So I know it works. I've been working on it for years, and I've told people over the years that I've been working on it for years, and oh yeah, they just think I'm some sort of weirdo dissident. I'm not. I do a lot of study. I understand Maxwell's equations, and nothing in this machine violates any laws of physics. It's just that we're approaching it from a different angle, and this machine that causes all this is very highly successful, and I would look at interplanetary velocities exceeding Mach 500. I've got no idea how fast it will go. Mathematical projections are that we should be able to go anywhere up to about 10% of the speed of light. The problem is it doesn't create its magic gravitational bubble. What it does is it accelerates an engine under you, so you will feel like you're on Earth. If you're accelerating at 9.8 meters per second, it will just feel like you're standing on Earth. So it actually creates an artificial gravity until you get into the hypercruise mode, and then you'll go into neutral gravity, weightlessness, that sort of thing. And notice I don't use the term zero gravity. Nowhere in the universe is there zero gravity. There's what I call neutral gravity, or heavy gravity, like on Earth. That's heavy gravity. This is what you'd be floating around in, out way past the Oort cloud. You'd be in neutral gravity there. But yeah, that's my little explanation. And as I said before, gravity just doesn't pull or push, it does both. When you fall into the stream of gravity, you start off here at 0 metres a second. This is 9.81 metres per second gravity field. It's pushing and pulling at the same time. It's just like throwing a rock, well not a rock, a bit of wood into a stream, and it takes time for that bit of wood to reach the same rate as the flow of the stream. So this is not a scripted video, it's just a rough presentation if anyone's interested. If anyone out there wants a gravitational drive, it's actually what I call an inertial gravitational drive system or drive engine, and my favourite name for it is the boomerang drive, because I want it to come back. Not only that, but it's a long story, but boomerangs sort of helped me in the early days to learn how to study flight. I used to throw boomerangs and catch them, and yeah, that was good fun, but it made me think about a few things. Anyway, thanks for watching. Give us a like, subscribe if you want, because in the future hopefully I'll be making a few more videos, and we'll go through maybe we'll go through Maxwell's equations to how they relate to this, which they do. This isn't really, if you want to know the full 12 dimensions, I'd have to write them out again. They're just properties of space. I don't believe in an empty space. I believe in, the old name was the ether, the new name is the space-time continuum. In a while they might bring another name, who knows. But anyway, this is all about space, gravity, and how we're going to get, well, firstly, we could get to the moon very quickly, we could get to Mars very quickly, but this inertial drive system, this has the possibility for us to send a probe to Proxima Centauri or any of those nearby stars. You know, they might be 4 light years away. If we could do it at 10% of the speed of light, you'd probably get there in about 40 years. Who knows, we might be able to even go faster, but my indoctrinated thinking is that at the moment I can't see us going faster than light. I could see us going about 10%, maybe that'll improve to about 50% in a few years once people develop my system even further. But I'm telling you right now, I beat all of you. I don't care what you say. This is nearly 40 years in the making. Obviously I can't show you the engine. I'll probably get in trouble for even just showing you this. You got no idea where I live and the pressures that I'm under. Anyway, thanks for watching. Talk to you later.